All right, next I want to look at how to actually calculate these moments of inertia for extended mass distributions. We've seen before that for a point mass, the moment of inertia, I, is equal to mr squared. Okay, so that's just a single mass that's going round and round in a circle at a certain distance away where we neglect the size of the object. But in general, what we can think of here is that if this is just some little bit of mass, dm, that's going round and round in a circle, then di, that little bit of moment of inertia for some vanishingly small amount of mass, is going to be our dm mass element. And so if we were to sum all of these up, what we had, say if we had several masses, and we wanted to know what the moment of inertia of all these masses was, then this would be I equals the sum of m sub I r sub I squared. So that would be m1 r1 squared plus m2 r2 squared plus m3 r3 squared. Sum in this case from I equals 1 to 3. Call this m1. And this being, let's say, our spin axis. So this would be r1. Here, this would be r2 to m2. And this distance here would be r3 to m3. And so we just sum them up. But what if we have a continuous array of masses? So in other words, we've got a little dm here at some distance r away. Let's make r the edge of, so in other words, what we're going to do here is figure out the moment of inertia of a rod about its end. So that would be like this, okay, rotating this thing about its end. Okay, and we already learned from the parallel axis theorem that I about the end is equal to I about the center of mass plus md squared. So if we knew what the center of mass moment of inertia was, 1/12 ml squared plus m, and in this case we would be moving from the center of mass, we'd be moving a distance d is equal to L over 2 to get to the end. That would give us 1/3 ml squared. So by knowing the moment of inertia at the center of mass, we could then proceed to figure out the moment of inertia about the end. But instead of doing it that way, I'm going to do it going back to basic principles, by integrating, by summing up. But we're summing up a whole bunch of little tiny mass elements. And so then this makes a transition to the integral of r squared dm. When you have an infinite number of masses that are at ever increasing distances away from the center of spin. And so the summation is kind of takes the place of, is in a continuous problem with continuous mass distributions, becomes the sum. And then that sum is over a bunch of little tiny mass elements that are infinitesimal in size. So each one of these dm's then has a certain r associated with it. Then this dm has a bigger r associated with it. And so we're going to need to integrate these mass elements over that distance. The only problem with doing this, though, is that m is our integration variable. And so that means we have to write r as a function of m, so we can integrate over r. and then we'll integrate over r. Okay, so how are we going to do this? Let's say the total length of this thing is L, and this is our pivot point. Well, first of all, we can introduce a quantity that we'll call our linear charge mass density, which is mass per unit length. Okay, and so the mass per unit length then, and let's assume it's constant, so that this is a uniform mass. Then lambda is a constant. So that would be equal to the total mass divided by the total length. It would have units of kilograms per meter. If it's constant, then that means that we have a uniform mass like this meter stick. So this meter stick then doesn't have more density of matter here than it does there. Okay, and that being the case, we can say that, okay, well, what happens, and listen to this argument carefully. What happens if I cut the mass in half? If I change the mass per unit length? The answer is no, because I've got half the mass divided by half the length. So this would also be equal to m over 2 divided by L over 2. It would also be equal to m over 4 divided by L over 4. It would be equal to m over 1,000 divided by L over 1,000. And so in the limit then, of mass per unit length, as the unit length goes to 0, what we end up getting then for this is just dm dl, or in this case, L is in the r direction. So I write that as dm dr. The derivative of mass with respect to length, or radius, is equal to the total mass divided by the total length, because the ratio, as we go to smaller and smaller mass elements until we take the limit as the length of that particular segment goes to 0, we call it delta L here if we went. And delta M is that part of the mass that corresponds to delta L. And the limit as delta L goes to 0, we just end up, by our definition for the derivative, being dm dl. So it goes all the way down. That same ratio is true even if we go down to an infinitesimal amount of mass divided by an infinitesimal length of the rock. And so that's our constraining function. And so that's critical here. Now this is equal to lambda. And so this gives us our constraining function. This is good. We can say that dm, written as a function of r, is just going to be lambda dr. So this is going to be mass per unit length times a little bit of length is a little bit of mass. Okay, so I can plug that back into this expression, and now I can integrate because I've got a constant times r squared times dr. Okay, so that was my goal here. I needed to write dm as a function of r, so that now I can do a single integration over r. This would be like a double integral, but it's not really double integral because there's no integration variable for r. Our integration variable is in m, so it's better to just write the dm as some constant times dr, and then we can integrate. And so this is going to be from 0 to L, because here r starts out at 0 and it goes to the total length L of the meter stick. So that's going to be lambda, so that's our moment of inertia. I is lambda times the integral of r squared dr from 0 to L. And so this is going to be r cubed over 3. So it's going to be lambda r cubed over 3 evaluated from 0 to L. So I then, now how do we translate back from lambda into factors that are relevant to the problem? Well, remember that the lambda is also equal to total mass divided by total length. So that's what you do to get lambda back into quantities that we're interested in this problem. So this is lambda L cubed over 3, or that's just equal to m over L lambda cubed over 3, right? I've just taken the lambda, I've replaced it with m over L times L cubed over 3. Then one of the L factors is going to cancel, and that gives us 1/3 ml squared. So I'm hoping that's going to be the same thing as I got doing it the other way. Sure enough, it is. And so that's a good starting point. But now the question is, how did I know that the center of mass moment of inertia was correct? We can also check that by more basic calculations doing the integration. And so we can't really know what that I center of mass is without doing the integral first. And so that's why we say here that integration is a more basic way to solve these problems, even though it's a lot more trouble than doing it with a parallel axis theorem. It's still a much more basic way to handle the problem. So we'll hang on to that very handy piece of information that lambda dr is equal to dm. And now let's find the moment of inertia about the center and verify that it's equal to 1/12 ml squared. So now here's our pivot point. The total length of this thing is L, but now we're starting from here. So this is our r equals 0. Okay, and so we're going to have to integrate then little dm's all the way from minus L over 2 to plus L over 2. That's L over 2 because it's all being measured in terms of the distances that we're talking about in this expression, r squared dm. Okay? It's going to have to be in terms of distances as measured from our pivot point. Okay, so here's our little dm again. Here's our r, but the r goes from minus L over 2 to plus L over 2. So you see that it's actually just the same as this setup here, but with different limits of integration. So I then is going to be equal to integral minus L over 2 to plus L over 2 of r squared dm. Okay, so that's going to be the integral of lambda r squared dr from minus L over 2 to plus L over 2. That's going to be lambda times r cubed over 3 from minus L over 2 to plus L over 2. Notice that everything's the same as it was here, except for the limits of integration. And so when I plug those in, I'm hoping that that'll give me the 1/12 ml squared that I'm looking for here. So I'm going to wait to plug in the lambda until after I'm all done converting the r into something that involves L, right? Okay, and so this is going to be lambda over 3. Those are two factors that stay constant times L over 2 cubed minus a negative L over 2 cubed, right? Because this is minus, and when you integrate, you're doing it between the endpoints, and so you subtract a negative. So it gives you two of those things. Right, so that's going to be lambda over 3 times 2 L cubed over, and then then down here, L over 2 cubed is L over 8. This is L cubed over 8, but times 2 because there's 2 of them. Okay, so that's going to be 2 times 8. 2 divided by 8 times 3 is 24. So that's going to give us lambda L cubed over 12. And so now that we're finally all done, and we've done all of the rest of our algebra, we've converted R into something that is between the endpoints here, then I can finally, in my last step, write lambda as m over L times L cubed over 12. And then that gives us our 1/12 ml squared. That then verifies that the moment of inertia of our thin rod rotated about its center of mass is equal to 1/12 ml squared. Next, I'd like to take a look at the moment of inertia for a thin ring. This one is going to be surprisingly easy. With a thin ring, we can break that ring up into little dm elements that are all a distance r away. So if we just broke this up into dm elements that are all a distance r away, then I would be the sum. Let's say we did this n times. So we had n different dm's. And this would be d, or we could call this delta m instead of dm, because it's not really an infinitesimal amount of mass. Then this would be delta m sub I, r sub I, from I equals 1 to n. So this is just going to be delta m1 times r squared, r1 squared, plus delta m2 r2 squared, plus all the way out delta mn rn squared. But all the r's are the same, because if this is delta m1 and this is delta m2 and this is delta m3 and that's delta m4, they're all at the same radial distance away. So r1 equals r2 equals r3, rn equals big R. So we can rewrite this then as just the sum of delta m sub I equals 1 to n, times r squared. Because the r squareds are all the same value and can be factored out and pulled and made a common factor for all of those terms. But then if I just sum up all the individual delta mi's and I've broken up the total mass into n of these, then all I've got left is just the total mass times r squared. So it's the same then as it would be for a point mass. For a thin ring of charge is the same as for a point mass, because every single mass element is like a little mass that's going around at that same distance away. And so if you just made that mass n times bigger, it would still be the same mr squared. But it's just spread out over that same radial distance all the way through. If we want to do this in terms of an integral, we could just say that I equals the integral of r squared dm. Okay. And then we can, because the r's are all going to cancel, we can make this really easy by writing this. I'm sorry, they don't cancel, but they're all a common factor that are all the same. This is going to be r squared times the integral of dm. Does that look similar to what we have here? R squared times the sum. Isn't that what an integral is? It's just a sum of an infinite number of different little tiny dm's. Okay, so in this case, we don't have to change our dm variable into something that involves r because the integration is not a function of r. It's basically a trivial integration, which the integral of dm is just m. Okay, and so we can write that then as mr squared. And we'd expect that that would be the same whether we broke it up into distinct elements that are all a distance r away, or we did a continuous process of letting one delta m blend into the next and making them all dm's. Okay, so that's a pretty simple result. But what if this, instead of being a thin ring, let's change that to a solid cylinder. Now this creates a little more of a problem. So our strategy here then could be to make this an infinite collection of our little thin rings. Okay, so if we had an infinite number of these little thin rings, each with radius r, until we finally get up to r equals big R. Then we could do the same thing that we did here. We could take the result for each of the little thin rings, say that I is equal to the integral of r squared times dm. And what's dm? Well, dm now, we're going to have to be careful with this. This dm is going to be the mass of a thin ring that has a thickness dr. So this is going to have a radius little r and a thickness dr. Okay, so although I'm giving actual thickness here to this ring, what I'm really talking about is something that is an infinitesimal quantity and has a vanishing small amount of radius associated with it. Okay, and so that's going to be then the mass of our little thin ring. Okay, and so the question then is, well, how do we sum up all these little bits of mass? Well, we can say here that, and here we're going to need to, because this mass encompasses an area rather than encompassing just a length. It's not one-dimensional anymore. It's two-dimensional. And so that means that our change of variables, because we still need to write dm as a function of r, so that we can integrate. Just like we did in that previous thin rod problem. But because it's two-dimensional, in 1D problems, like the rod, then we have lambda is equal to dm dr. But here it's 2D, like a cylinder. So now we want a sigma that is equal to dm d area, where A is the little bit of area. That is associated with dm. But that is also going to have to be total mass divided by total area, which is pi big R squared. So this is total mass of the whole cylinder, and this is the total area of the cylinder. But we want it to also be equal to a little tiny bit of mass divided by a little tiny bit of area. And so that's similar to what we did here. Remember, this was equal to either total mass divided by total length, or dm dr, or dm dl. Here, total mass over total area, or dm dA. So the question is then, how do we write a little bit of d area for a cylinder? Well, we know that the area is equal to pi r squared. So d area is going to be equal to 2 pi r dr. Okay. And so if that's the little bit of area, and sigma is mass over area, then dm is going to equal sigma times 2 pi r dr. So that's what this little bit of mass is here. A little bit of mass in that region is equal to the mass per unit area times 2 pi r dr. Now if you don't believe that, or that seems too abstract to you, let's try just snipping it and stretching it out. If we cut it, we stretch it out, then the length of this thing is going to be 2 pi r, right? Because that's the circumference of a ring that has a radius r, times the thickness, which is dr. So that's just the area of a rectangle is the base times the height. And so d area, if the thing is infinitesimally thin, is just going to be 2 pi r dr. So we have dm dA times dA, that gives us dm. So we've got something now that we can sum up. We can sum up all these little infinitesimal mass rings, infinite number of them, from 0 to r. And so this was the key step then, is to see that dm is equal to sigma times dA. And then we can plug that back into this expression to get dm strictly as a function of r. That becomes sigma times 2 pi r dr. All right, so now we're ready to turn the crank on this. And now we're going to integrate all these little rings from r equals 0, so that's a ring that is barely there at all the way out to big R. So this will be the integral of r squared times sigma 2 pi r dr, 0 to big R. So at this point, I think you can all do this problem. If this were in your calculus class, you'd say, oh, this is too easy. There's got to be more to it than this. That the trick in a physics class is to understand where these expressions are coming from and to be able to write them down and understand and see that they make sense and that this really is the same thing as a little bit of mass of that ring. Okay, so when we do this integral then, we're eventually going to take sigma and write that sigma is equal to total mass divided by pi big R squared, because that's the total radius of a cylinder. Okay, but we don't want to do that yet, because that's going to mix us up. We're going to have big R's and little r's in here. So we want to just pull that out and make that a constant to begin with, times 2 pi. And then we're going to be integrating from 0 to r of r cubed dr. Okay, and So that's going to be equal to 2 pi sigma times big R to the 4th over 4. Right? Because this is going to be little r to the 4th over 4, but then evaluate it from 0 to r. So it'll be big R to the 4th over 4. And then in our final step, now we take the sigma and we plug that in as mass divided by pi big R squared. There's a 4 in there, and then this is going to be r to the 4th. Okay, so the 2 and the 4 cancel, the pi's cancel, and so this gives us a factor of 2 left down here, but that's 1/2 mr squared, which is the moment of inertia of a cylinder about its center of mass. Now, what if we wanted to find the moment of inertia of the cylinder about some other point? Let's say this point here. Can we integrate that? Well, it's going to be a much tougher problem. So for something like this, although it can be done, and as a matter of fact, Isaac Newton did this kind of an integral for a sphere to show that you could think of all of the mass of the sphere as being located at its center. What we're better off doing here is, once we have the center of mass moment of inertia, is to just go back and use the parallel axis theorem to figure out what the moment of inertia would be about some other axis. It's not as easy as with the rod problem, where you just change the limits of integration. Here, you've got a whole different geometry. The only place where you've got the kind of symmetry that allows for an easy integral is to integrate out in rings that are from the center. And I'm not saying you can't do it any other way, it just becomes much more difficult to do it some other way.